In this video, we're going to finish looking at simple linear regression. So one of the benefits of simple linear regression, after we've concluded that we have a useful model, what we can do is we can then use that model to estimate what's happening on average or to make predictions. And so in this section, we're going to look at how we can use the model to do that. So the model can be used to estimate the mean of a response variable corresponding to a particular value of a predictor variable, or can be used to predict a particular value of the response variable corresponding to a particular value of the predictor variable. We're going to talk about the difference between these. So we're going to go with that example that we've been looking at all along with our delinquent minors, and recall that we already fit this model and got the following. And we're going to pretend that we found that this was a useful model. We did see it had a pretty low R-squared in the previous note set, but for the sake of illustration, we're going to proceed forward. So the first thing we're going to do is we're going to estimate the average delinquency index for all convicted minors who have an IQ of 115. So a couple keywords to notice here are the words estimate, average delinquency index, or how the response variable is acting on average for all convicted minors. And this is what we call an estimation problem. So to estimate this, what we're going to use is our fitted line that we have up above. So we're going to estimate that to be equal to putting in the estimates for the intercept, the slope, and then we're interested in IQ equal to 115, and that gives us an estimate of 23.6494. We could alternatively do what's called a prediction problem, where we predict a convicted minor. So no, this is a single minor's delinquency index. So we just have one minor here. We're not talking about all convicted minors. And it ends up, to get the predicted value, we actually just do the same thing again. So the estimate and the predicted value for each of these are the same. The difference is going to come into play when we look at the accuracy of the estimate and the prediction. In other words, when we create confidence intervals around each of these. And so on the next page, we have some information that talks about the sampling errors, because remember, we always want to talk about our sampling errors, which gives us an idea of the variability in our statistic, and this is under these two different scenarios. And then we have the two different formulas for the confidence interval. So this is the interval we're going to use when we have estimation problems. And this is the interval we're going to use when we have prediction problems. And so we're going to look at each of these and you'll see how the intervals differ. So the first one we're going to look at is the estimation. And so this question says find a 95% confidence interval for the average delinquency for all convicted minors. So the fact we're looking for an interval for the average and we're talking about all, in other words the population, that's how you know that this is going to be an estimation problem. So we're going to want to use our estimation formula, and so that formula is as follows. Right. And most of these values we have found previously. I have them up top. The only one that is new is the XP, and the XP is the value we want to predict or to estimate at. So in this case, it'll be the IQ of 115. Now, one thing to notice is that critical value, that T alpha divided by 2, that is still going to come from a T distribution with n minus 2 degrees of freedom. Or in this case, that will be 18 minus 2, or 16 degrees of freedom. So it ends up, that is the exact same value that we found on our previous example from our previous note set, and we found that that t alpha divided by 2 was equal to 2.1199. So you find that the exact same way. Now, if we had asked for a 90% or 100%, well, not 100%, 99, then of course that value would change. It just happens that we have the same degrees of freedom on our t distribution, and we're finding the same level of confidence as that previous problem. So let's plug in all of these values. So the y hat is what we found on the previous page. The t value we just discussed. S we have found previously, and it's given up above. N is our sample size, so we had 18 in this case. We're predicting at the value 115, and I'm running out of space here, but previously we had that x bar was equal to 103.2222. And then we're going to divide all of this by sum squared xx. And this is all under that square root. And if you put this in your calculator, you'll get the following. It results in the following interval. Now in lab, I am going to show you how to get this interval using both SAS and R. And so I will go ahead and warn you, when you go to compare these values with what we find in lab next week, there is a little bit of rounding error here. And that's because, again, we're only looking at things up to 2 decimal places, and so I just want you to be aware of that when you get to that lab. These values are going to be slightly different. So as always, we need to interpret our interval. So our interpretation is we are 95% confident that, remember what we're estimating here is average delinquency index. And we're estimating this for all convicted minors. And we're doing that for those minors with an IQ of 115. And that value will be between, or that average is between, the values that we found up above. So again, the confidence interval, or the estimate, that's giving an estimate for the average delinquency index for all minors with an IQ of 115. Now in contrast, we could also look at a prediction problem. But one thing that I do want to make a comment on is always be careful not to extrapolate. So be careful not to extrapolate. So the reason that we could find this confidence interval at 115 is because that is within our range of IQs that we have observed data for. So make sure whenever you make these intervals that you are looking at X values that are within the range of your observed data. So again, this was an estimation problem. In contrast, we could look at a prediction problem. And so here, notice we're not going to create a confidence interval, we're going to create a prediction interval. And this interval is going to be for a single minor's delinquency index if the minor has an IQ of 115. So again, we're not looking at an average for all, we're looking at the index for a single minor. And so I went ahead and I plugged in the formula and got the interval here. The math is very similar to what we just did on the previous page. The only difference is, notice the formula is slightly different, and in that square root we do have a little bit of extra, and we'll talk about why that is here in a moment. Notice that our interval that we get is much wider than the interval that we got for the estimation problem. So let's look at its interpretation. So here, since we have a prediction interval, we say we predict with 95% confidence that a convicted minor, so again, we're talking about an individual here, and in particular, we're looking at a convicted minor with an IQ of 115, will have a delinquency index between 6.62 and 40.67. So notice this range is huge. And so a couple comments here. For the same predicted value of x, the predicted intervals are always going to be wider than the confidence intervals. With the confidence intervals, we're talking about what's happening on average, so we're able to control that variability. When we start talking about individuals, there's a lot more variability that we have to account for. And so what happens is our intervals end up getting wider. And so take a moment, read through these comments here. All right, so the last thing we're going to talk about is residual analysis for the simple linear regression. And I'm just going to briefly talk about this idea. And the reason for it is we use a residual analysis to determine whether or not our model assumptions have been violated. Later, after we've talked about multiple regression, we're going to spend a lot of time talking about how to perform a true residual analysis. So here, I just want to briefly mention some things that are done, but I don't want to spend a whole lot of time on it at this point because, again, we're going to spend a lot of time on it later on. So if we want to check the assumptions stated regarding that error term, what we do is we're going to look at the residuals. And so remember, there are 4 assumptions. We have that those errors are normally distributed, they have a mean of 0, the variance is constant for different values of x, and all the pairs of errors are uncorrelated or they're independent. We can check them using the model residuals. And so just to recall what the residuals are, the residual is the difference between our observed y and our predicted y. So we calculate our residuals by looking at each of our observed values of y. So thinking in terms of our example we've been using throughout these notes with the IQ and the delinquency index, we had 18 observations, so we can calculate 18 different residuals. And so how we do that is, notice if we look at our observed y's, which are observed delinquency indexes, we could use our model to predict what the delinquency index would be for different levels of IQ, and we get the predicted values. So each of the residuals is going to be the difference between the observed and the predicted. So in this case, if you took the 26.2, you subtracted off the 24.8906, you would get that residual. And what we do to check our assumptions is we're actually going to look at plots of these residuals. Now, by default, R gives a really nice what we call fit diagnostics for the model. So we're going to look at SAS output here. In lab, I'll show you how to make these in R. So SAS gives a lot of different fit diagnostics. For right now, we are only going to focus on these 3. And again, later on, when we give a much more detailed treatment of the residual analysis, we'll look at some of these other plots. So here we have a list of some plots to look at, and so we'll go back up to the top and look at each of these. The first one is to plot the residuals on the vertical axis against the predictor variables on the horizontal, and we'll call this plot 1. This type of plot helps to see if the distribution of the residuals is uniform around 0, and that would suggest constant variance. It's also used to check if the linear model assumption is appropriate, and so the points should look like random scatter. So looking up at the top, that's this plot right here. And so when we're looking for patterns, we might look for dips or horseshoe shapes. We also want to see things randomly scattered about 0. So in other words, we wouldn't want to see a bunch of points tightly clustered here, for example, and then spread out further. Now, in this case, we only have 18 observations, so we do have to keep that in mind. I do notice looking here It looks like there is a point that's kind of out here by itself, so that point concerns me just a little bit, but this doesn't look terrible considering that we have that small sample size. The next two plots is we can look at histograms, and probability or quantile plots are used to assess the normality of the residuals. So these are going to be plots 2 and 3. So here is your quantile plot, and here is your histogram. So looking at both of these, I don't see any large deviations from normality. Our QQ plot, we generally want it to be fairly linear. It does look fairly linear. Again, we do have that one point that I'm a little bit concerned about that I probably want to comment on. But again, only have 18 data points. And looking at my histogram here, it is roughly symmetric. It does have a slight skew. It's not perfect, but what you'll find out when you work with real data, especially with small sample sizes, you're not likely to get perfect histograms or perfect QQ plots. So we're looking for large deviations that really make us question that normality, especially when we've got small sample sizes. And then the last thing we could look at is if we have time series data, then we could look at a plot of the residuals to see if we see any patterns through time. If we do not have time series, then it doesn't make sense to look at this. So in this particular case, we've got these observations from 18 different minors. None of this has been taken, we're not looking at the same individual through time. This is not time series data, so we're not going to worry about that for this particular data set. And then finally, there's a small comment here about how we can use standardized residuals to look to see if a point is an outlier or not, and we can talk about what we need to do with those. But again, for right now, this is all I really want to say about the assumptions is just, just this little piece, because again, we're going to spend a lot of time on this topic later on. And this is going to conclude this note set.